Okay, good, fine. Yeah, unfortunately, Christian Schmidt he was at the lattice conference and he had to urgently go home. So he asked me to give his talk, and that's what I'm going to do. This is his talk he sent to me yesterday, and I'm more or less reading it to you, except two pages which I added. And well, since this is the last and third day of this conference, I couldn't resist to pay a tribute to one of the big guys here in Plymouth, and that for a change is not just called, but it is Sir Francis Drake. Every second traffic light is named after him, is my impression. So I may remind you that he was a buccaneer. A buccaneer is a pirate, but a pirate with a license. And QE stands here for Queen Elizabeth. So they shared a business model and both profited from that very much. But what is perhaps not so well known is that he was the first British skipper who sailed around the world. Later on, he was admiral in this battle against the Spanish fleet, the Armada. The English did not really defeat them. They lured them on sands between Dover and Ramsgate, and then where the ships all sank and what was left over had to sail around Scotland, and that did the rest. So I would say we end perhaps this conference here with the motto, with Sir Francis to new shores. Since that is online, I didn't dare to write something like in thimbles across the ocean of complex configurations. Anyway, so Claudia has given a very broad overview, which does not leave me much to say because I have to see already this kind of phase diagram with the experiments, which are trying to locate in the end locate the critical point if there is a critical point. We are going to analyze this by means of Taylor expansion. The reason to do that is twofold. First of all, the Taylor expansion, of course, is invented to describe the pressure at non-vanishing chemical potentials. So that's something we can do. But the byproduct of this expansion, so to speak, are these fluctuation coefficients, which Claudia had already discussed a lot. So that's the phase diagram you have seen. And some motivation is coming from the beam energy scan, which was mentioned in the previous talk. And here's a result for the cortosis. There is some non-trivial structure here that is one of the signals which made people optimistic to see some deviations from equilibrium thermodynamics. No, that's not right. From non-trivial behavior, which might in the end lead to some evidence for a critical point or not. So the big obstacle is the sign problem. We have discussed that here at length. So the talk of Christian comes into two sections, basically, namely number one, the Taylor expansion of the equation of state. We have a new round of analysis with reduced error bars for the coefficients of this equation of state. And of course, you can use these coefficients to then study these cumulative ratios. That analysis is not yet complete with the new round of data. Okay, so the Taylor expansion is, as was explained already, as simple as it can be. What you have learned in school probably, the Taylor expansion in the chemical potentials for baryon number, for electric charge, and for strangeness. And on the lattice, you can compute these coefficients here at mu equals 0. So that is the way to bypass the sign problem. And you can then compare it with these fluctuation variables, which in principle can be measured in experiments. And that then will, the comparison then will give you indications about freeze-out temperatures at chemical potentials. So to repeat what was mentioned already in the previous talk, the mean over the variance is given then by chi1 over chi2. Chi1 for any quantum number here, whether it's B, Q, or S. The cortosis is the third order derivative with the ratio to the second order one. And then there is this funny thing that was, did I say cortosis? I meant skewness. And here is this fourth order derivative, which is related to the cortosis. So these are things the experimentalists can in principle measure from the figures Claudia had shown already. Okay, to remind you, the hadron resonance gas model, formulae which were also on the transparencies of the previous talk, with the Boltzmann equation going from here to here, because this is the sum over all k, and look at this k2 Bessel function which has as an argument k here. Now k2 is proportional to e to the minus x, so if you increase k, and in particular if these masses are of order 1 GeV or even higher, then they're exponentially suppressed to a very, very good degree, so that you can reduce this sum over k to the lowest order k equal 1. That, of course, does not really work for the pions, and maybe the kaons also have a problem here, but Claudia checked that, and it seems that for the kaons, the Boltzmann approximation is also okay. If you work in the Boltzmann approximation, then some of these susceptibilities become very, very simple. Look at, for example, the nth derivative with respect to the baryon chemical potential, and since the baryon number of each baryon is 1, this is just K2. So if you then look at ratios in the hadron resonance gas model Boltzmann approximation, if you look at ratios of these chi-Bs, say chi4 over chi2, they're just 1. Okay, you have seen this figure already, showing that at mu b equals 0, we are done, more or less, at least with staggered quarks, 2 plus 1 staggered quarks. So now comes the deviation of this from mu b equals 0 and stuff. So let's first look at that chi2b, the leading difference. So that is this figure, new results with the continuum extrapolation. Then the next order is the kurtosis times variance shown here. And here you see already that there is, even in the transition region, which is the yellow region here, there are large deviations from the hadron resonance gas model prediction. Whereas in chi2b, the hadron resonance gas model seems to work well. So if you assume that so we leave it at that. Now the fourth order, the next order then, chi6 over chi2, comes with a coefficient from the factorials, which is 1 over 2 times 1 over 360, so it's suppressed very much. And then you look at these numbers here, they seem to be of the order of 1, so in our case we are not yet really done with the 6th order coefficients, because to our taste these error bars, in particular at temperatures below the critical or pseudo-critical one, are still too large. Nevertheless, if you then compute the pressure, and this is just the difference of the pressure at finite mu b and the pressure at mu b equals 0 is subtracted, then for mu b over t, the 6th order does not really make a big difference, because here we compare in open symbols and red curve, we compare the 2nd order with the 4th order, which is filled symbols and blue, and you cannot really see the turquoise band here because it's under the blue line. However, for mu b over t equal to 3, the situation is different, and it seems that one needs at least the 6th order in this quantity. Right? And that is the background of the statement that the pressure seems to be well controlled for mu b over t less or equal than 2, maybe even 2.5, and that corresponds then to center of mass energies down to 12 GeV per nucleon in the plot I've shown in the beginning, and the plots Claudia has shown. Okay, now let's introduce, I did not mention it, I'm afraid. So this was at mu s equal mu q equals 0, but the experimental conditions are of course different, as Claudia mentioned already. So we have certainly strangeness neutrality, and then there is an isospin asymmetry, so there is a typo, where this value of r is often taken to be 0.4. Of course, that can be questioned. some people argue that in the middle of the fireball created in such a heavy ion collision, there should perhaps be isospin symmetry, and then this R would increase to a value of 0.5. So this number is coming from the initial conditions, just computing or counting the number of protons versus the number of baryons in the lead nucleus or in the gold nucleus. Now these conditions can be expanded in powers of these three chemical potentials, and then if you solve for these two conditions, then you have two conditions for mu q and mu s, which can then be solved in Taylor expansion again, and that is also what Claudia showed. If you look closely, then these coefficients S1 and I think S3 did not yet appear, but S1 and Q1 appear. Okay, so then you can express this this pressure as usual in this series up to second order. That's these terms, and if you now plug in mu s as a function of mu and mu q as a function of mu b, you end up with this expression here, and all the sum of these derivatives times these coefficients, in this case only the lowest order coefficients contribute, of course, is called P2 in the following plot, which is shown here. Now again, we have then this Taylor expansion, but just in UV. And here you see the lowest correction, the P2 correction, which are these data points here, for the case that there is strangeness neutrality and that this ratio between quarks between charges and electric charges and baryon number is 0.4, and you see a considerable effect between those two conditions. The upper line here is the one where mu q and mu s is equal to 0. That's the P2. The same holds for the P4 coefficient. So there is a considerable strangeness dependence in this pressure. Below, we show P2 for various values of this R variable. So here is 0.4 in particular and 0.5. So there is not much difference between those two cases. So the conclusion here is there is a mild isospin dependence over B. Okay, so that brings me to the total pressure. Here is the one for mu q equal mu s equals 0, and here is the one for the experimental collisions of lead-lead or gold-gold heavy ion collision, and note that the scales here are different. Okay. So the second chapter of Christian's talk is now to look at these cumulants, as Claudia did also extensively. Now here we have the Taylor expansion a series between mean versus variance. So that of course starts at mu b. Then here is the skewness, which also starts order mu b. And here is the kurtosis, which starts at order mu b to the power 0. Okay, and then with these corrections, of course. Okay, so as was said in the previous, or as was really pointed out and emphasized in the previous talk, we want to compare with the RHIC experiments in particular. And the RHIC experimenters don't know mu b, but they know, of course, what energy they have dialed. So we need a relation between, we need a relation between the central mass energy and mu b. And that comes from this quantity. Yeah, that's the mean of baryon number, say, normalized to the variance, and that's given by chi1b over chi2b, of course, at any mu b. But if you go back, this quantity starts at mu b with corrections of order mu b squared. Okay, so to lowest order, you can treat this ratio here as the mu b. So then in principle, or the experimentalists also do that, they measure this quantity, and then they have an idea of the chemical potential they are at this given center of mass energy. And the conversion factor in the hadron resonance gas model is just 1 plus higher orders, and in QCD one can compute this number here, L1 to B1, which is again coming from the Taylor expansion. and that is shown here. This number is shown here in the continuum extrapolation. So plugging this in, measuring that experimentally, you know the value of the chemical potential at this mass energy, which is a nice thing to do. Now, second thing, we go now to skewness. So we have two leading order in this ratio where the UB dependence, the leading UB dependence of the skewness is divided out because it's normalized to the mean. Then you have again a number which comes from QCD, which you can compute, plus order mu b squared, plus the order mu b squared is traded here now for the mean of the baryon number divided by the variance squared from the previous transparency. So one can look at experimental data like here, where this quantity is shown as a function of this quantity. Both are measured by star in this plot, so this is purely experimental results. So they can do a fit of this quantity, and that can be compared with the lattice result at a given temperature. All these coefficients here are of course temperature dependent. So that is another way to possibly extract the freeze-out temperature from experimental data. So now I forgot what the next plot is. Here you see again, if you want to go to the next order, that involves 6 order coefficients, and this, at least in our data, is error loss. Okay. So one can, of course, continue that game and go to kurtosis, and there are also interesting results on the QCD side. This transparency is, however, also meant to bring to your attention something which was also on one transparency of Claudia. That is, of course, something which needs to be further discussed and checked. One thing is we are, of course, assuming thermal equilibrium. All the lattice numbers are coming from normal lattice simulations which rely on thermal equilibrium. That, however, can be tested if you compute and measure various tumulants of various orders, and that should be all consistent. Nevertheless, one can try to look into non-equilibrium effects, and there is a paper by Schwagatu on this, which is mentioned here. Then in many of these experiments, experimental plots, no, I started the sentence the wrong way. The experimentalists do not measure baryon number, they measure proton number, because that's something they can do. So in these plots I showed before, for instance, in this one, this was not really the average proton, the average baryon number, but the average proton number. So there is an issue whether you can do that, and there are a couple of papers. Some of them were also mentioned in Claudia's talk, discussing whether you can take the protons as a proxy for the baryons. And of course, the experimentalists are very, very difficult, so you have to discuss acceptance cuts in the PT distribution and all that. So I cannot say anything about this. I'm just a lattice person. So conclusions and summary. So these are the conclusions and the summary by Christian. I didn't do anything of it for that, and maybe you just read it. Thank you.
So we thank both Edwin and Christian, and we have time for questions and comments.
Everything is clear. This is great. Huh? You want to know more about some of that, just right?
Well, just a very general question. How do you understand non-equilibrium effects?
How do I understand non-equilibrium?
Or how much non-equilibrium actually do we need? Or I can't help it if I see two temperatures coming out of the same statistical ensemble. I always think that non-equilibrium effects.
One of the astonishing findings of experimental or phenomenological findings concerning these heavy ion collisions is that the thermalization time is so damn short. It seems to work that after one Fermi oversee, the thing is in equilibrium so that you can successfully apply hydrodynamics pictures. Now, of course, there is a lot of work to do to understand this equilibration, and for my taste, it was the wrong subject of Alexei Kopola's talk at the Lattice conference last week. However, he was emphasizing that more has to be done on the equilibrium phase of equilibration phase of the ion collision experiments. On the theoretical, say on the QCD side, people are of course working in linear response to theory on the transport coefficients and to see whether one can obtain reliable lattice results from there, which then could be fed into hydrodynamic models again. Sorry, but more I can't say. Behind.
I wondered if you could enlarge more. You made a comment about the ratio between the net charge in a collision and the net baryon number.
Yeah.
And you said the number's not 1.4 in the central region.
Yeah.
Where does that come from?
You collide. I mean, the 0.4 is just you count the number of protons in gold or in lead and compare it to the number of protons plus neutrons, and that gives you 0.4. So that's a condition in the initial state. But if you have these, now I need my hands. Sorry. If you have these oblate heavy nuclei colliding, then of course the baryon number is going down the drain, so to speak, down the bean pipe. So it's not clear that this ratio, which is sitting in the initial conditions, is also persisting in this fireball in the quark-gluon plasma, which is sitting at central rapidity. So some people say this quark-gluon plasma should be more isospin symmetric. For instance, Reinhard Stock is insisting on that always when he gives talks like that in Germany. I mean, maybe the experimentalists can say something about it.
This is a comment on Kurt's question. The issue of thermalization at the beginning of the collision, which ensures validity of hydrodynamics, is a completely different issue from the one that we are addressing here. This happens in the hadronic phase, and it's the question of how does the system fall out of equilibrium again. And we are not talking about falling out of thermal equilibrium, we are talking about falling out of chemical equilibrium, which means the abundance ratios start freezing out while the momentum distributions still continue to evolve. And to answer Kurt's question, how strong are the non-equilibrium effects, is actually very hard. You have to do a full dynamical modeling, and the modeling of the hadronic phase is at the moment not in its best state. And that was one of the reasons why the DOE funded this beam energy scan theory program that is supposed to bring the theory forward over the next 5 years to a point where we can actually address questions how strong would be dynamically evolution-driven non-equilibrium effects on these fluctuation ratios and ratio fluctuations and so on.
Yeah.
There was Yonder and then Bob.
Okay, so I think it was a follow-up on I guess it was partly commented on already, but this charge to baryon number, I guess that should show up in some difference if you try to measure the temperature from central rapidity versus forward rapidity distributions. I don't know does anyone know if there's any experimental evidence of differences there?
Well, I don't know, but I mean, with what kind of lattice results would you compare them?
So
yeah, I mean, there are studies about the rapidity dependence of the chemical freeze-out temperature and the centrality dependence of the chemical freeze-out temperature, and all in all, these effects are quite small. You know, on the other hand, going from 0.4 to 0.5, if you want, in terms of isospin symmetry, you also don't expect that much of a difference. So I think this is rather mundane if you look at it as a function of rapidity. But I think with respect to what Kurt also was saying, let me just make one comment. It is very interesting to look at three independent quantum numbers and look at them as a function of freeze-out temperature. But it's by no means trivial, for example, that the charge and the baryon number should give you the same freeze-out temperature if you think about non-equilibrium effects. So the fact that it does that at this point, at least to the precision that we get from that QCD, is quite interesting, and it's also important.
Absolutely. No. Okay. So thanks again. That's the good point. On time, so we have plenty of time for discussion. Thank you. Next talk, once again, Claudius C.